Good morning. Today we will continue our lecture on support vector machine. In the last class, we saw how to work on linearly separable data set. Now, in many cases, there will be noise in the data so that a linear decision surface cannot separate the positive and negative points. We will see how support vector machine can deal with it. So, if we look at the linear SVM formulation that we did in the last class, we had this optimization function which required us to find the weight vectors W and B such that the margin width is maximized. So, the margin can be written like this 2 by W. So, this is maximized subject to M constraints corresponding to each training instance. So, for each training point, I equal to 1 to M, we had yi wxi plus b is yi times wxi plus b is greater than equal to 1, right. This can also be written as, instead of maximizing 2 by W, we can maximize its reciprocal, that is half W. So, W is actually root over W dot W. So, we can minimize this. Rather, we can minimize W dot W. Okay. So, we can look upon it as a minimization problem subject to M constraints corresponding to the M training examples. Now, this particular formulation enables us to deal with only those training instances which are linearly separable, but it may be that the data is not linearly separable. If you look at this slide, we see that we have two classes, blue and red, and this data cannot be linearly separable. There could be a non-linear decision surface which separates the data, or in this case, it may be that the data points are noisy so that there is no clear separation of the points. So, what we will like to do is, we will like to extend the definition of maximum margin so that we can allow these non-separable points. Now, we have to now redefine our objective function. Earlier we were trying to minimize W dot W. This is no longer sufficient. So, we have to be able to have a decision surface which makes some errors. So, if we have the points, these are the red points and these are the blue points, we want to be allowed to make a decision surface which does not clearly separate the positive and negative points, so that there is some error in this. But if we have this error, we cannot deal with these constraints that we have looked at. So, we have to make some changes. So, first of all, we have to make changes to our optimization function. So, one way of looking at it is, we want a decision surface which looks at two things. One is maximizing the margin, which corresponds to minimizing W dot W. Secondly, we may say we want to reduce the number of misclassifications. That is, we want to minimize the misclassified training points or minimize the training error. So, we may be tempted to write this objective function as w dot w plus number of training errors, and maybe we can use a parameter c to control how much importance we give to this part and this part. The problem with this formulation is that it is no longer a quadratic objective function, so that we cannot use a QP solver to solve this optimization problem. So, we have to look for an alternative formulation. In the alternative formulation that we look at, we do the following. We assume that, given some points, we are able to define a margin, and then we try to, let me just redraw this. Suppose this is my decision surface, and this is a margin that we are looking for, and these blue points may be here, may be here, whereas the red point may be here, may be here. So, we can see that these points, we have an error. So, this point, the blue points ideally should be on this side of the margin. So, we can see that this blue point and this blue point are in error, whereas this red point should be ideally on this side of the margin. So, these red points are in error, right. Corresponding to each of the points which are not correctly classified, assuming a particular decision surface and the corresponding margin, for each such point we can give a penalty, and the penalty can be given proportional to the how far it is from its correct position. That is, if we take this blue point, what is the minimum amount by which I have to move this point so that it is correctly classified. So, this can be obtained by dropping a perpendicular from this point to this margin. Similarly, for this blue point, for this red point we have to move in this direction to get it correctly classified, and for this we have to move it like this. So, what we will do is that with every misclassified point we will associate an error or a penalty which is the slack variable. Suppose this is the point 1. So, we can associate xi 1 corresponding to this point, xi 2 corresponding to this point, xi 3 corresponding to this point, xi 4 corresponding to this point. So, these are the penalty that we are associating with the points which are in the wrong position. The xi values associated with the other points will be equal to 0. Now, we can rewrite our objective function as w dot w plus c times the sum of these penalty functions. So, we can write c times sigma xi k. So, k equal to 1 to m, where m is the number of training examples. So, if you look at the slides here, we can rewrite our formulation as minimizing w dot w, which corresponds to making the margin, looking at the size of the margin, plus c times distance of error points to their correct zones, and we achieve it by adding slack variables xi I. So, for each point which is misclassified, we find its shortest distance to the correct zone, and this corresponds to the xi for that variable. For the other variables which are correctly classified by this particular decision surface, xi values are equal to 0. Now, let us look at this slide. So, we have this is our decision surface whose equation is given by wx plus b equal to 0, and upon normalization there are two these are the two margin lines, Wx plus b equal to +1 and Wx plus b equal to -1. And here are the 3 points which are wrong, 3 of the points which are wrongly classified, and corresponding to each of them we have the variables xi1, xi2, xi3. The margin width is given by 2 by root over w dot w, which we want to maximize and which corresponds to minimizing w dot w. Adding the penalty due to these slack variables, we get the minimization function to be w dot w plus c times sigma k equal to 1 to m xi k. So, this is what we want to minimize. Earlier the constraints that we had is yi w dot xi plus b greater than equal to 1. Now, you see that this constraint will no longer hold for those points which are in the wrong zones. So, we can rewrite this constraint as yk yi w xi plus b greater than equal to 1 minus xi k, right, for I equal to 1 to m. Actually, for the blue points which are wrongly classified, we can write w dot xi plus b greater than equal to 1 minus xi k, and for the red points we can write w xi plus b less than equal to minus 1 plus xi k, and we can write it together as yi into w xi plus b greater than equal to 1 minus xi k for I equal to 1 to m. So, this is the formulation of the maximum margin classifier when we wish to handle noise. Now, in order to solve this equation, we can find the Lagrangian of this quantity. So, the Lagrangian with parameters w, b, xi, alpha, beta, and we get it as half w dot w plus c sigma xi I plus sigma I equal to 1 to m alpha I yi into x dot w plus b minus 1 plus xi I minus sigma I equal to 1 to m beta I xi I. So, actually there is another set of constraints. In this case, we have a set of m nonlinear constraints, and we also have m constraints xi I greater than equal to 0 for I equal to 1 to m. So, we have 2m constraints, m constraints of this type and m constraints of this type, and therefore, in the slide we can see the Lagrangian of this quantity as half w dot w plus c sigma xi I plus, please look at the slide, sigma I equal to 1 to m alpha I times yi x dot w plus b minus 1 plus xi I minus I equal to 1 to m beta I xi I. Alpha i's and beta i's are the Lagrangian multipliers, and they are greater than equal to 0. Now, given this Lagrangian, we can look at the dual formulation corresponding to this formulation. So, in the linear SVM, we wanted to find alpha 1, alpha 2, alpha m such that this quantity sigma alpha I minus half alpha I alpha j yi yj xi dot xj is maximized, and such that the constraints were alpha I greater than equal to 0 for I equal to 1 to m and sigma I equal to 1 to m alpha I yi equal to 0. In the case of noisy SVM, this quantity remains the same, but the constraints change. So, earlier we had alpha I greater than equal to 0, we have now alpha I is between 0 and c for I equal to 1 to m. The second constraint remains the same. So, the dual formulation of this noise accounted SVM, this constraint is changing. Alpha I is now lying between 0 and c. The rest of the formulation is the same. Now, given this dual formulation, we can find the solution to the classifier. So, this is called noisy, linear SVM, or most commonly this is called soft SVM, because we do not have a hard classifier or a hard decision surface that clearly separates the positive and the negative points. And the solution of this soft margin classification will be similar to the solution that we got earlier. For example, those data points which have non-zero corresponding Lagrange multipliers alpha I, they will be the support vectors. And as you can see, the support vectors will be those points which lie at the margin as well as those points which lie in the incorrect zone. And the solution to the dual problem is given by W equal to sigma I equal to 1 to m alpha I yi xi. Alpha I is non-zero only for those points which are support vectors. And once we find the values of alpha I, we can find the value of b from any one of those points. So, b equal to yk into 1 minus ik minus sigma alpha I yi xi xk. So, for any of these k, we can find b after we have found the alpha i's. For classification, now once we have found the solution of this equation, we can use it for classification. For classification, again we use the similar formula fx equal to sigma I equal to 1 to m alpha I yi xi dot xj x plus b. So, x is the test point and I corresponds to to those points for which alpha I is non-zero, which are exactly the support vectors. So, again we see that in order to find the classification of a point, we actually do not need to compute W explicitly, but we can just apply this formula, and in this formula we need to find the dot product of the test point with the x value of those points which are support vectors and multiply by the corresponding alpha I yi value, sum it up and add b to this, right. So, the formulation is pretty straightforward and quite simple and easy to apply. Okay. So, this is how we deal with soft classification or soft SVM. However, if the decision surface, so we are able to account for noise and come up with classifiers which do not exactly separate the positive and negative points. However, the classifier decision surface is still linear and cannot handle those cases where the decision surface is actually non-linear. How to handle that in some cases we will see in the next class. Thank you.